Alrighty. Let's go ahead and get started. So, today what we're going to be doing is using what's called the squeeze theorem. Some places they'll call it the sandwich theorem. I've heard it squeeze theorem, sandwich theorem. Basically, the idea either way is we are taking two functions that we know the limit to, we're squeezing them together so that we can find a third function we don't know the limit at a certain point. And this is gonna feel kind of weird, but what I want to do is I want to sort of talk about it algebraically, and then once we've done a couple algebraically, we'll do some visually just so you can see. I've got Desmos pulled up on the side, and I'll show you what I'm talking about, how they actually get sandwiched together. All right, so let's start off with a thing. So let's say I want to figure out the limit as x goes to 0 of this thing, x squared times the sine of 1 over x. And you look at that and you say, well, okay, this is a problem. And the reason this is a problem is because of this part, the sine of 1 over x. If you remember, we talked about this a few weeks ago. The sine of 1 over x sort of does one of these as it goes to 0. Just sort of hangs out there 5 ever and then goes on its merry way. This area, this is where 0 is, and we don't want that. We don't want this mess because this doesn't have a limit at this spot. But we need to look. So what we're going to do is we're going to say, all right, well, if this does have a limit, we should be able to find two different functions that we can sandwich around. So we're going to be like, okay, well, let's put one like this. We're going to put the less than or equal to symbols here. And we're going to find two functions. Doesn't matter what they are. So that these two are the same we're going to 0, so that these two are the same as 0. And if f of x and g of x are both the same, this thing that's sandwiched in between them also has to be the same. And that's sort of the key here. And really what it boils down to is you've got a really complicated function and you're going to try and make it not so complicated. What do you mean? Well, there's a specific reason I have this sign of x bracketed and called attention to. And that's because this thing has a maximum and a minimum y value that pops out, right? Sine, the range on the sine function, is from -1 to +1, right? The lowest sine function can pop out as a -1. The highest that a sine function can pop out as a +1, right? If you think about the unit circle on the xy plane, this is the lowest number you can get on the y value, and that's a -1. This is the highest number, right? That's a +1. So what does that mean? Who cares? Well, we do. And the reason we care is because since we know this fact, let me scooch this up a little bit. Since we know this fact, we know that this function, regardless of what x is, this part, the biggest this can get is 1, right? And the smallest it can get is -1. So why don't I just make sine of 1 over x equal to 1? Isn't that just x squared? Right? Just said, okay, the sign's going to be a 1. So that's x squared. And that has to be as big as this function if it's not the same, right? And then the same thing with -1. If the least that sine can ever be is -1, then this is the least that this could ever be, ever. So if this is true, which it is, then we can take the limit as x goes to 0, because that's what we're trying to find, right? We're trying to figure out what this is at 0, and we can't do it just by itself. But now with the help of these friendly bookends here, as x goes to 0 here, well, that's just 0, right? As x squared goes to 0, that's just 0. Well, now look, if x squared sine of 1 over x, if that limit is less than or equal to 0 and greater than or equal to 0 at the same time, it's got to be 0 too, right? So using the sandwich theorem or the squeeze theorem or whatever you prefer to call it, using this, you know that the limit as x goes to 0 of this monstrosity here, x squared sine of 1 over x, is equal to 0. And so, like I said, this is not going to be a particularly long lesson because it's pretty much all the same. And a lot of these are either going to be extremely intuitive or they're going to be something that you can't do by intuition. You have to basically do trial and error. So what I want to do is I want to stop sharing my screen there and I want to share my Desmos view here. I want to share with you all this Desmos. So what I have here, this is a blank XY plane, and I've got this function I was just talking about. Now, I don't know if you can see, it looks kind of almost like a straight line until you start zooming in on it. You get really close up in here, and it starts to get all wibbly wobbly, right? I don't know if it's easier to see now. Let me maybe zoom in further, right? You see how it's, when you get really close to 0, it's super duper wavy. And it's like, okay, well, I don't know what's going on. And what we said was that if we look at x squared and negative x squared, let me bring in x squared. You see how this greenish line hits the tops of each and every one of these. It's always either bigger than the blue line or equal to the blue line. And then let's look at negative x squared. And if you see, the green line and the purple line here squeeze together the x squared times sine of 1 over x. You go through and it wibbles in there, and no matter how tight you squeeze in, you see that the blue line stays in the middle. And if I were to zoom out, you know, this is how the function sort of hangs on. It always does something like this. So visually, the squeeze theorem here is an incredibly powerful thing. It does show you how you can take two functions and just smush them together with this guy in between and show what the value of the limit has to be, because it's pretty clear that the limit as x goes to 0 for x squared, the green one, is 0. It's incredibly clear that the same thing holds true for negative x squared. But if this one's always in between, Well, then at that spot, it had better be exactly that. So I've done that. Let me show you a couple more. Here's another one. So this black one that I just put up, you can see is x squared times cosine of 1 over x squared. And again, you sort of see that the green line and the purple line sort of hang out right along the edges of that black line. And as we zoom in, we can see even better how that looks, right? As it wibble wobbles in there faster and faster and faster, it stays in the middle, right? No matter how tightly we try and push it in, we see that the line in the middle actually just sort of smushes into infinity. And it's really cool. I actually didn't check this out before, but the example that I was given was the 1 over x squared graph. I wonder if 1 over x would give the same thing, and it does. You see how it stays in? It doesn't move quite as fast. All this exponent does is it controls how fast the thing wibble wobbles back and forth. I just put it to the 6th power, and look at that. You see how it just immediately goes into this big blur, right? Because it's oscillating faster and faster and faster, but it's always staying in between x squared and negative x squared. It doesn't matter how tight you make it. I don't care if it's to the 15th power. This is probably going to make it freak out. Yeah, look at that. Isn't that cool? It just starts to blur immediately. But it always stays within the boundaries of x squared and negative x squared. And that's all we're talking about here. I've got a couple more examples. Like, for example, this one. This one is x squared times e to the sine of 1 over x squared. So what you can do is you can do the exact same thing like what we did with the x squared times sine and x squared times cosine and all that, is you can say, well, the sine is only ever going to be between 1 and negative 1, so let's make sine 1, and let's make that our top, right? You see how it stays on top? The blue line here stays on top of the red line. Even up here where it seems to meet somewhere, the red line just sort of skips off and then goes back the way it came, right? But if you see all this wibble wobble right here, always bounces off the parabola and then comes back down. And we're going to see that, so if e to the negative 1, that's 1 over e, that's why I have it written like this over here, comes up the other side. And again, you see it hits. The Desmos even knows to make a little point there. That's the intersection where the two lines meet. But it always stays in the middle, right? The orange line always stays in between the blue and the green. Always. So now, there's a couple that are kind of like trial and error. This is one of those things where it's like, oh, well, you just look at it and you see, and no one ever just looks at it and sees. Somebody ends up showing them. So I want to show you this one. This is one that we've talked about. I've got to zoom way out because I'm super far in right now. I'm like in the hundredths. So here's sine of x over x. And we talked about this last week or the week before. And we said that the limit as x goes to 0 is 1. And the thing of it is, I'm telling you that. And so it's like, okay, well, it's 1. So I'll just, anytime I see, I'll just put 1. And that's not very satisfying, right? So we need to get a better idea as to why it's 1. So here I've got it zoomed out a little bit more just so we can look. And so the two functions that you can use, because the problem is what you would want to do is you would want to use 1 over x and negative 1 over x, right? And I'm going to have to do them down here. 1 over x, which it, I mean, it does. It does do what we said it should do. But the problem is that the limit doesn't converge at 0, right? If I got rid of these, if I try and find the limit as x approaches 0, they go away. So we can't use those. And the same thing with the other one. Like they don't. There's no value at 0 that we can work with, so we can't use those. And so at some point, somebody figured out using some other thoughts. Well, maybe we're not concerned like the whole way. Let's look at this. It never gets above 1, right? Well, so let's put 1 at y equals 1. Look at cosine. Yeah, it doesn't, it cuts through over here, but we don't care about the whole function. We just care about when it gets close to where we want, right? So if we see the purple line gets sandwiched in between the orange line and the black line here. And so since as x gets pretty close to 0, sine of x over x stays less than or equal to 1, and cosine of x stays less than or equal to 1. We can sandwich this together and we can show that the sine of x over x does always give us 1. And actually, if I remember correctly, I did tell you that we can make it work for any sine of something over something. As long as the something stays the same, this sandwich still holds, right? You know, it may have to get really close before it gets in there properly. I don't know if you can see slowly the purple line is coming closer to that red line. You have to zoom in real quick, real far, but that's the idea, is that they all converge at 1 here. The last one I wanted to show you is another one where it's like, well, let's look for it, because what we would want to do, and again, I'm way zoomed in. What we would want to do, this is x times sine x. What we would want to do, if we were following the rules that we talked about earlier, is we would want to use x and negative x. Here's the problem. It has to stay sandwiched. I mean, it kind of does sort of do that, but it has to stay sandwiched between this one being on top and this one being on bottom, right? If this is on bottom over here, it has to stay on bottom. If this one is on top over here, it has to stay on top. And what someone realized is, wait a minute, hold on. Doesn't this just look like the absolute value, right? The absolute value is a v, right? And it's like this top part and this bottom part. So instead of doing x and negative x, let's do absolute value of x. That way the top part stays on top. And negative absolute value of x. That way the bottom part stays on bottom. And what's really cool is as you zoom out, it totally does what we wanted it to do, right? It always stays in between the top there and the bottom there, no matter how far we zoom out. I think this just looks cool as heck. I don't know about you. So that's the sandwich theorem, folks. Basically, all it is we're gonna say, here's the top function, here's the bottom function, the middle sort of, as we zoom in, gets closer and closer to where they're the same. And at the spot we care about, we don't have to worry about the middle function anymore, because we can't do that on our own. But what we can do is we can follow the functions that act as the bread in the sandwich and follow them, and they should be the same thing.